Welcome, my name is Janus. I have a background in both computer science and chemical engineering. Nowadays I love to work with the Rust language, which is growing very fast and gives safety guarantees. It has modern accessible tools and methods for programming.
I'm Jonathan Ayala, a chemical engineer with a master's in process systems engineering. I'm dedicated to driving progress towards a sustainable future through the optimization of key industrial processes. The Haber-Bosch process is a cornerstone in our field. It's essential for synthesizing ammonia, which in turn produces the fertilizers that sustain the global agriculture and support the global food supply.
That's a really great application example. And as a first step, we implement a simulation of the Haber-Bosch reaction. In later videos, we'll plot the results and add some interactive elements. But let us start with what is the Haber-Bosch process. Now that we have set the stage, it's time to dig deeper into the chemistry that drives the world. Jonathan, why should we care about ammonia?
Ammonia is vital because it's a building block for making fertilizers, which in turn are crucial for global food production. Without the Haber-Bosch process, we wouldn't be able to sustain the world's population.
Yeah, that sounds very pivotal indeed. Can you break down this process for us? Well, what is happening in the chemistry there?
Absolutely. At its core, the Haber-Bosch process is about combining nitrogen from the air with hydrogen typically derived from natural gas under conditions of high pressure and temperature to create ammonia. It's a marvel of chemical engineering that hinges on precision. Too much hot, too much temperature, or too much pressure, and then we lose efficiency.
Yeah, I see. That's probably a very good candidate for optimization. So, and can you tell me some mind-blowing facts about the process?
Well, considering this, the Haber-Bosch process uses so much energy. It accounts for around 1% of global energy consumption, and every percentage point represents a massive environmental footprint and underscores the need for sustainable energy solutions in chemical manufacturing.
That's really a significant impact, but what that does mean for our environment then, right?
It's a double-edged sword, team. While we're creating the foundations for food security, we're also grappling with environmental cost. This process is a major consumer of fossil fuels, leading to substantial CO2 emissions. That's why innovating for a more sustainable Haber-Bosch process isn't just an option, it's an imperative for our environmental future.
Yeah, but understanding is always a first step to improvement, and that's why I propose we now dig into the modeling of the Haber-Bosch process. So, what do we do?
We use concentration balance equations to model the reaction dynamics. By simulating the process, we can experiment with conditions that could lead to more energy efficient process.
I see.
For example, in our simplified model, we can investigate how temperature affects the reaction rates.
Yeah, I think that's a really great idea. But before we do that, let's dig into how such a reactor looks like in the real world and under which condition is it working in the Haber-Bosch process.
Okay, so the Haber-Bosch process is governed by several key factors, like the kind of catalyst, the operating conditions, especially temperature and pressure are critical for this synthesis process. All this happens in a black flow reactor, or for short, a PFR, where the reactants convert to products while moving through the reactor.
I see. So for our simulation, we will just integrate over the length of the reactor in small intersectional slices. But what is the math behind this, and how do we enter with a simpler model?
Okay, so here we have a partial differential equation for the system, or for any system in general. We neglect the first term with the first derivative, and with that we assume the concentration doesn't change with respect to time. So the system is in equilibrium, and so we can simulate the startup or shutdown processes with this model, with this simplified model.
Alright, that just means left term disappears. We assume there are zero changes over time, but over the length. But what is with the velocity, the right term? Can we neglect it?
Well, the flow speed can give us insight about the length of the reactor. But given the level of simplification of our model, we can set it up to 1. Because it's more practical to have the length of the reactor as a conceptual parameter rather than a precise measurement.
Very well. Let's have a look on the next slide. Yeah, that's the Arrhenius equation at the bottom. It is used to describe rates in many systems that depend on activation energy and temperature, like our reaction system, right?
That's correct. And at the top, you see the reaction system consisting of 2 reactions, the forward reaction and the backward reaction.
Yeah.
And they are in equilibrium.
I see. So, well, for the forward reaction rate, we will use the Arrhenius calculation. And in the backward case, we will just let it depend on the forward reaction rate with a factor. But let's see the system of equations. These 3 equations, that describes the concentration changes over time. And to see that, it's pretty common for chemical engineer. But Jonathan, can you explain what these equations mean in detail?
Sure. So each row describes the change of the concentration for each component. The left terms are modeling the forward reaction, which follows a non-elementary rate law. And the right terms model the backward reaction, which follow an elementary rate law. So now I'm curious about how to implement this in Rust and why Rust, Tim?
Yeah, that's a very good point. And let me highlight that Rust is already transforming the development of safety critical software. It guarantees safety without compromising performance. It will also fasten the time to market for those safety critical software because, like in automotive, you have to go through a series of revisions for the specification for safety. And that's much easier if there are more guarantees from the language directly. And yeah, but I invite you to read about it in my blog, and we will link it in the video descriptions.
Okay, wonderful. Yes, I will definitely give a look to it. So let's move on to the implementation of Rust.
All right. All right, after the discussion with Jonathan, we're ready to simulate Haber-Bosch. But first, I want to dig with you through the learning materials. Therefore, we fire up a browser and go to the homepage github.com/DASB/Pragmatic Rust for engineers. And here you find a code repository, which are our learning materials. You have to click on code, and now it depends. If you install the environment with our install video, you're fine to use Git. Otherwise, you can also download your zip and stick to whatever environment you use for development. So I copied the URL here for Git, and now we open Visual Studio Code. And in Visual Studio Code, we want to open a terminal. All right. And there we just type git clone, and we copy with right click the URL, and we choose the video 0.1 folder. And now we reopen code in the video 0.1 folder. And that's the point where we are in our learning environment. All right. So here on the left side, you see some files, and we will start by opening the markdown file, and it's a text file, right? And you can install another extension. It's called Markdown Preview. And see, like when you hit F1, you can then type in commands in code like open preview. It's already on the top in my case, when you have a nice formatting. All right, and here are some information about the learning materials. What I want to highlight here is like you can just watch the video, you can go through the code by yourself, like the solution. You can try to solve this now without me helping you, and have a look at hint.rs, which contains some example code. Or you could like say, okay, I'm completely hard, I don't even look in hint.rs, and you can always switch, right? Okay, but let's see the task for the Haber-Bosch video 0.1. It's another markdown file in the Haber-Bosch directory. And I will also open it with a markdown preview. Here we have some learning goals. First, we want to be able to simulate and model this process with an ODE-Solver. And in the end, critically investigate the results. But we also learn a lot about Rust, like simple things like how to call a function, how to set up a data structure, but also complex things like we will use a trait to integrate the ODE-Solver, and we will talk a bit about the type system. And we will do this now by shortly have a look at the hint.rs file. So that always has like some example code that helps you when you're not familiar with Rust to see some examples that you may need to solve the things. And we have like scattered around add to-do markers. And what you can do then is like follow those to-dos. And here's an important one for highlighting the uniqueness of Rust. Like here we give a reference to data 1 and we are not moving the ownership. And if you like change this, like you comment this out, you would now change the ownership without the ampersand. And that's very important for Rust to give it safety guarantees, like it's allowing it to check if things are borrowed and so on, so that there's only ever one writer or several readers on a data. And you will get like this kind of errors, borrow moved of value and so on, and then you're probably missing a reference somewhere. So that's not in the scope of this course to talk about everything, but there are very good learning materials already, and we have some references here. Just check it out. All right. Okay. So first task is we want to add dependency to the ODE-Solver, and there's also a link to the website of the ODE-Solver, and very early it tells you to add this line to your cargo toml. And if you remember from the install video, cargo toml, it's just like information about your Rust project. So we will add that there, say one time cargo build in the terminal. In your case it will take some while, and then you have the dependency compiled. Next step, back to the tasks. We want to implement a function that calculates the reaction rate via the Arrhenius equation. Call it and output the results. Okay, so I think we will hit main now. Get rid of the hints because they are linked here. And yeah, so just a slight reminder. We had this slide here, so maybe we can just keep this open. And I also have something prepared in the clipboard. I will just add a comment here with some constants so that we can copy them around. And if you remember correctly, Arrhenius gives you the reaction rate. We need this. And for that, we need, for example, a constant, which is the gas constant, the universal one. It's called R. We use a type here, it's F64, which is like floating point numbers with 64 bits, which are 8 bytes. And we just copy this value here, okay? All right, so we have the gas constant. Then we define in main a variable, which is the activation energy, and it's just 27.1. I don't copy that. And now you see there's additional info. We get the F64 here. It's just infos code provides for us that we know in a static type system what is the actual type of the variable. And the next one, it's the exponential factor. We will just write 2 dots, right? Multiplied with 10.0 dot, and now we have the possibility to call a function, and we will call pow e, which is like the power function, and the parameter is an integer. So we give a -2 here, and we do not use a dot. And by this, Rust knows, okay, this is an integer, and we can just check that power -2, and you see it's an I32. So we can make it this way. Okay, I get an error message. So what is it saying? Oh, you must specify a concrete type. Yeah, okay, what is the problem here? Rust does not know what this type is, 10. It could be either F33 or F34, so we can just like postfix it with the right type. That's rarely needed. It's quite cool that it came up here. And then we have like our variables together, and we can implement a function. So we can make this function public. We use the fn keyword. We call this Arrhenius. And now in the signature, there are 3 arguments. First of all, the activation energy. Secondly, the exponential factor A, which all are like this F64. And we have the temperature, right? Which is also F64. And we want to return, that's why there's an arrow, another integer. And well, I hope you remember the equation. It is A times the exponential activation energy, divided by the gas constant mal the temperature. And now we just omit the semicolon, and by this Rust knows, okay, that's an expression and it is a return value. That's really like, this is really great when working with if statements and so on. We will see this later. Okay, everything seems fine so far. So now we can call this function and store the result. It will be called RF for reaction rate forward, and then we just can use nearly the same parameters. So we called it exponential function here, and we don't have a t, but yeah, it is 400. We define it as in this case for 400, and then we can use the println statement that was also in the hello world files, and say rf equals to rf. And now we're ready to hit the terminal, run cargo run, and we see, okay, it's some small number with a 2 somewhere after the comma, like 0.0002. Okay, we will now switch to source control, which is our Git. We say we have a feature here, Arrhenius equation calculation, and we commit. Yes. All right, next 3 is like struct Haber-Bosch model. We should put our constants in there, like have a data structure, and we want to output it with a debug trait. And we will also just implement the system trait of the ODE-Solver crate. So let's start with our own first custom struct. We make it public, we call it Haber-Bosch model, and we have a reaction forward rate, which is an F64, and we have a reaction reverse rate, which is an F64. And yeah, to create it, we can simply use let model, and then we use Haber-Bosch model, have this parenthesis here, and I use now Control and C to get like some recommendation, and the quick fix for this error is like fill the struct fields. We do this, and then we see, okay, there's a RF, and there's a RR double colon to do. And RF is like, it's the same name here in this scope and here. So when, let's just give an example. When we would call this rate F, then here's this change, like RF double colon is mapped to art rate F. And we will just come up with a constant here for the reverse reaction rate, which is 2 times the one of the forward reaction. Now we have a model, and we want to print our model, right? So let's give it a try with a println macro. And when we try this, there's another error. And the error states, oh, moment, there's a trait missing. We need the display trait. So this, with a placeholder and a variable, it only is working when struct implements a display trait. We won't do this because there's no default implementation for display, but we can derive a trait which is called debug. And debug has a default implementation for outputs. The only thing we need to change here is like we have to use another placeholder. We use a double colon and a question mark in this parenthesis. And now when we switch to the terminal and we run it, we can see, okay, it prints our model. All right. So the next step is like we want to have the system trait, sorry for that, of the ODE-Solver's crate implemented for our Haber-Bosch model. And we will look now how this works. So first of all, they say have a type alias definition. We will do this. And this fixes our suites now needs well, because we have also a vector of 3, because we are working with 3 concentrations, right? So we just put it here. And we get an error because it doesn't know what is vector of 3. Control dot again gives like hints what you could do, and we will just import vector 3 from the ODE-Solver's crate. Okay, so we have the type state. Next step is we have to come up with a system definition, and that is a trait which has a generic v. Yeah, so this is a state, like what we call state here. And then we have a function that is our equation system. Okay, so we implement this trait now for our Haber-Bosch model. So therefore we write implement system with state for Haber-Bosch model. We use this parenthesis again. And we have to import it, control dot, import system, and now here on the top we have like 2 possibilities. We use the one from the ODE-Solver and it gets added here. Great. So we have that, control dot again, which says, okay, we have missing members of the system state trait. Please implement them for us. So here we are. And now this is nothing else than our equation system here. And we have to now transform it into code. And for this, we calculate dy, which is like the derivative. For the first index, it is just -1 times self rf times y from 0 times y from 1 plus 1 times self reverse rate times y from 2 with a power of 2. And that's not working because I forgot the dots here. As you remember, without the dot, Rust thinks this is an integer, and then it's not sure which type to use. Okay, so just add the dots, and now we have to repeat this for the other. So that's it, just one dot forgotten. Okay, now we have the states here, and yeah, I think that's a good point to check if we're still able to build.
We have a lot of warnings. Normally I would get rid of the warnings, but it's all about not use variables or like wrong names. Like Rust wants you to use lowercase variable names. So we now commit a feature. System equation reality for ODE-Solver. Commit. Yes. Last but not least, we want to use a DOP853 solver and like output this Y out, and we want to check with an iterator how the concentration are in each step. So first things first, we need to like come up with a solver. We now call it stepper, and let's check the documentation. So this is the wrong one, but the one we wanted to use was called oopsie 8.5. So I just use the right type here, right? And I have to import it with control dot. I get this. Now we need, we have a model here, x0. We start at the beginning of our reactor. We go to 200 units, whatever those units are. We use 0.1 for dx. I think it's just the stepwise what we get as an output. So for y0 we come up with a new variable, which is our state, and we want to have 1 unit of nitrogen, 3 units of hydrogen, and 0 units of ammonia in our in our starting condition. And this is like just some tolerances. Now we use something very, very small here. Okay. So in the stepper, it should be mutable. That is new. Mutable means the variable can change. Otherwise, you have a read-only instance. Now let's get the result out of this, and we can match the result. A result type is like either OK with a variable, which is the actual result, in our case the state, and we will just print the state. Oops, there we need the quotes. Or it is an error, in which case we will just return, I guess. Oh, that's not working. Then we print an error. Oh, I forgot to give the error type here. So now we print the error and we give it a try with cargo run. And you can see, okay, we have like 93 function evaluation and it's doing something. So we add again a feature calling ODE-Solver. Nice. Okay, hard cut. Because I found errors in our code. First, I misspelled the Arrhenius. It's a minus activation energy. And second, this formula here, it is wrong because the right-hand side is a negative because we're producing ammonia in the forward reaction, and that is a backward reaction where we lose ammonia. So both things are changed now. You can also clear the screen in the terminal. And now we want to get a variable y out. Therefore, we access the stepper It has a function called yout, and now we can just print the result, okay? And there we see our results. Something is wrong, the parentheses are missing. Okay, so, and as you can see, okay, there's still an error somewhere. Yeah, in the Arrhenius there was also the exponential term missing. So that should it be. Like how many errors can you make? Yeah, that looks better. Like in the end we have like 0.15 of nitrogen, 0.46 of hydrogen, and 0.18 of ammonia. And yeah, what in the task is like, there's a task. We want to find out what is the sum of everything. Therefore we use an iterator and the map function, and we just sum up the components. Okay, and we will see more elaborate iterator use later, and we use a collect function. Especially we have to give a type argument, so we say we want the collect function into a vector of f64s, and actually I think this has to go here now. Okay, and this changes our output, and we see, okay, we end up with like 0.18, which is absolutely fine. Where's the start, by the way? That is, like we start with 1 and we lose somehow the thing. We're not losing it, it's just a matter of units. But let's discuss this with Jonathan, because in the next video we want to get this concentration plot, and we wanted to have like the purities, like fractions, that you see how much percent ammonia is in there.
Hi Jonathan, can you clarify about the units we are using throughout our work?
In our component balance equations, we have moles per unit volume. It's important to note that this addition or this sum up of concentrations may not add up to 1 along the reactor.
Thank you for the clarification, Jonathan. And if you have any questions, feel free to leave a comment.
And if you find this video informative and useful for you, we'd appreciate your recommendation.
And we hope you tune in for the next time. Till then, bye.
Bye, thanks for watching.